Let's say we have a zero order reaction where A turns into our products. And when time is equal to 0, we're starting with our initial concentration of A, and after some time period t, we would have the concentration of A at that time. So we could express the rate of our reaction. One way to do it would be to say that the rate of the reaction is equal to the negative change in the concentration of A over the change in time. And another way to do this would be to write the rate law. So the rate of our reaction is equal to the rate constant K times the concentration of A, and since I said this is a zero order reaction, this would be A to the 0 power. And any number to the 0 power is equal to 1. Therefore, the rate of the reaction would be equal to K times 1, or the rate is just equal to the rate constant K. So the rate of a zero order reaction is a constant. It's independent of the concentration of A. Next, we can set these equal, right? We can say that K is equal to the negative change in the concentration of A over the change in time. So we have the negative change in the concentration of A over the change in time is equal to the rate constant K. And next, we can think about our calculus, right? Instead of writing change in A over change in time, we're going to write the rate of change of the concentration of A with respect to time. We have our negative sign in here, and then we have our K on this side. So we're ready to think about our differential equation, and we're going to multiply both sides by dt. Let me go ahead and multiply both sides by negative dt, so then we would have dA on the left side, right, and then we would have negative k dt on the right side. And we're ready to integrate, right? So we're going to integrate on the left. K is a constant, so we can pull it out of our integral on the right. And we go back up here to refresh our memories about what we'd be integrating from. So we'd be going from time is equal to 0 to time is equal to t, and from our initial concentration to our concentration at time t. So we plug those in. So we're going from time is equal to 0 to time is equal to t. And then for our concentration, we're going from our initial concentration to our concentration at time t. So we have some easy integrals here, right? What's the integral of dA, right? That would be, of course, A, or the concentration of A. So we have the concentration of A, right? We are evaluating this from our initial concentration to our concentration of A at time t. On the right side, we have another easy integral of dt. That's just t. So we have negative k t, right, from 0 to t. Next, fundamental theorem of calculus, right? So we would get the concentration of A, right, minus the initial concentration of A is equal to, on the right side, that would just be negative kt. So we get negative kt here. And so this is one form for the integrated rate law for a zero order reaction. All right, we could rearrange this. We could move the initial concentration to the right side, so we would get the final concentration is equal to negative kt plus the initial concentration of A. And so this is just another way to write our integrated rate law. So here's the integrated rate law for a zero order reaction. And if we look at the form of that, right, it's y is equal to mx plus b. So y is equal to mx plus b. So we would put time on the x-axis, right? If we graph time on the x-axis, on the y-axis we have the concentration of A. We're going to get a straight line, and the slope of that line, right, the slope of that line m, the slope is equal to negative k. The slope is equal to the negative of the rate constant. And the y-intercept would be the initial concentration of A. So if we just sketch out a quick little graph here, right, let me put our axes down. So we'd put time on the x-axis, right, so down here we'd have time. And on the y-axis we have our concentration of A. We're going to get a straight line, all right? We're going to get a straight line, and let me see if I can, let me just go ahead and switch to a straight line. I don't want to draw one in here. So we got a straight line like this, okay? And the slope of this line, right, the slope of our line here, the slope would be equal to negative k. Right, so once again, we can see that from up here, right? The slope is equal to negative k, so m is equal to negative k. And our y-intercept, of course, would be the initial concentration, right? This would be the initial concentration of A. So this is the integrated rate law for a zero-order reaction. Next, let's think about the half-life. So remember, the half-life is the time required for the concentration of a reactant to decrease to half of its initial concentration. So when the time is equal to the half-life, t1 half, right, we'd plug this in for t. The concentration of A, when time is equal to the half-life, would be half of the initial concentration, right? So the initial concentration divided by 2. So that would go into here. So let's rewrite what we have. We now have the initial concentration divided by 2 is equal to negative k times the half-life plus the initial concentration of A. So let's solve for half-life. On the left side, we have the initial concentration of A divided by 2, or 1/2 of the initial concentration of A. On the right side, we have the initial concentration of A. So this would be 1/2 minus 1, which is negative 1/2. So negative 1/2 of the initial concentration of A is equal to negative k times t1/2. So solve for t1/2, or our half-life. t1/2 is equal to, this would be the initial concentration of A divided by 2 times k, 2 times the rate constant. So here is the half-life for a zero-order reaction. Notice, if you increase the initial concentration of A, right, if you increase the initial concentration of A, what happens to the half-life? They're directly proportional. So if you increase the initial concentration of A, the half-life should increase. So the half-life should increase. Let's look at an example of a zero-order reaction, and this will help us understand this idea of half-life a little bit better. So our example is the decomposition of ammonia. So the decomposition of ammonia into nitrogen and hydrogen. And this reaction occurs on the surface of a metal catalyst. So let's say we're using platinum here. So on the left, let's call this situation 1 on the left. We have a piece of platinum, right? So imagine this is our platinum surface. And since the reaction occurs on the surface of the platinum, the ammonia molecules have to be in contact with our platinum surface. So let me draw in some ammonia molecules in blue here in contact with our platinum surface. Remember, this is a zero-order reaction, right? So the rate is equal to the rate constant times the concentration of ammonia to the 0 power. So increasing the concentration of ammonia doesn't affect the rate, and this picture helps us understand that a little bit better. If you increase the concentration of ammonia, right, I'm adding some more ammonia molecules in here, you're not affecting the overall rate of the reaction because the ammonia molecules I just added are not in contact with our platinum surface, right? So only these down here are in contact and are able to react. So we increased the concentration of ammonia, but we didn't have any effect on the rate because the rate of the reaction is limited by how much surface area of our metal that we have. All right, so that's situation number 1. Let's think about situation number 2 over here. We have our platinum surface, right? And let's draw in a bunch of ammonia molecules. So here we have some in contact with our platinum surface, and then here we have even more, right? We have even more ammonia molecules, and obviously most of them are not touching the surface of our metal catalyst. Right, so we've increased the concentration, we've increased the initial concentration of A, right? Of course, A here is our ammonia. And so we must increase the half-life. That's what we learned up here. If you increase the initial concentration of A, right, you have a longer half-life. And that makes sense because our reaction has a constant rate. The more molecules we have present, the longer it takes to consume half of them. So we have all these molecules up here of ammonia that aren't touching our metal surface. And so we're limited by our constant rate. And so it's going to take a lot longer, right, to consume half of the molecules in blue, right, in situation number 2. So that's comparing situation number 1 with situation number 2. We've increased the initial concentration of A, and therefore we have a longer half-life.